Hello everyone. So our process is designed to monetize 1,000 kilograms per hour of raw post-consumer PET waste flakes, which equals an annual capacity of 8,000 tons over an 8,000-hour operating year. To maximize resource efficiency, a massive water recycle loop of 6,829.99 kilograms per hour is utilized, minimizing fresh water intake to just 169.84 kilograms per hour. At a glance, our neutral hydrolysis reactor utilizes a zinc acetate catalyst at a 1:67 mass ratio to PET to convert the waste into terephthalic acid and ethylene glycol. Downstream to a PTA filtration system removes solids and fines to obtain high purity TPA products, while a distillation system separates the EG and recovers the processed water. Furthermore, a 95.63 kilograms per hour of unreacted PET is completely recovered from the effluent and recycled back to the feed, improving the overall conversion efficiency and ensuring a circular economy with zero net solid waste. So this details operational layout maps out the 10 precise steps required for chemical conversion and purification. Step 1 is the pre-treatment, where heater and pump elevates our feeds to restrict reaction condition of 240 degrees Celsius and 36 bar. Step 2 is the RCSDR reactor, where zinc acetate catalyst hydrolyzes PET into TPA and EG. The step 3 is a severe service slurry valve, which safely drops the pressure from 34.2 to down to 1.5 bar, inducing an energy-saving flash cooling. Step 4 is the flash drum, instantly separating volatile flash vapors from heavy liquid solid slurry. Step 5 is the forced circulation crystallizer, cooling the stream to 90 degrees Celsius to force a dissolved TPA to completely crystallizes out. Step 6 is the hydrocyclone, exploiting a 13.3 particle size ratio to separate unreacted PET from TPA slurry. Step 7 is the candle filter, which recovers the solid TPA product from liquid stream. And step 8 is the vapor recovery condenser, which condenses the EG flash vapor and merges it with the liquid filtrate. Step 9 is the distillation column, separating the water overhead from recycling, leaving high purity ethylene glycol at the bottom. Step 10 utilizes product cooler to drop the final ethylene glycol product to a stable 25 degrees Celsius for industrial storage and export. So the final high-value chemical product specification achieved by this process layout are highly optimized. Our primary product, terephthalic acid, is recovered as a solid crystalline powder with a controlled particle size ranged to 50 to 150 micrometers, collected directly from the candle filter solid outlet. It leaves the line at the extraordinary 0.999 solid fraction, representing a 99.99% purity, with less than 0.1 residual moisture content. It is produced at a steady rate of 779.22 kilograms per hour, achieving a total TPA recovery rate of 99.67, making it ideal for direct repolymerization into virgin plastic. The high-value co-product ethylene glycol is recovered as a clear liquid from the distillation bottom, cooled to 25% at 1 bar. It flows out at a steady 291.8 kilograms per hour, representing a 99.99 EG recovery rate. By successfully avoiding corrosive acid and bases, utilizing pressure letdown for low energy cooling, and achieving an absolute zero waste circular loop, this process proved that PET monetization is highly efficient, profitable, and sustainable.
Moving on to the reaction and conversion analysis, our plant utilizes the neutral hydrolysis of PET via ester bond cleavage. Stoichiometrically, each polymer repeat unit contains 2 ester linkage, meaning it reacts with 2 moles of water to fully depolymerize into 1 mole of TPA and 1 mole of EG. With a raw PET feed rate of 1,000 kg per hour, our RCSDR reactor achieves a single pass conversion of 90.437%, yielding 781.833 kg per hour of TPA and 292.09 kg per hour of EG. What makes this design highly sustainable is that the remaining 9.563% of unreacted PET is entirely recovered by the hydrocyclone underflow and recycled back to the feed, leaving zero net plastic waste. Furthermore, by avoiding harsh acidic or alkaline conditions, we completely eliminate common side reactions like TPA decarboxylation or DEG deformation. Now let's look at the reaction mechanism and catalyst performance. The hydrolysis follows a nucleophilic acid substitution mechanism at the ester carbonyl carbon, consisting of 4 core steps. First is the catalyst activation. Zinc acetate acts as a mild Lewis acid, coordinating with the carbonyl oxygen to increase the electrophilicity of the carbonyl carbon. Second is the nucleophilic attack. A water molecule attacks this activated carbon, forming a tetrahedral intermediate. Third is the chain scission. The intermediate collapse, cleaving the ester bond to split the polymer chain into carboxylic acid and hydroxyl termini. Finally, progressive depolymerization. This continuous cutting action breaks the long backbone down into short oligomers and eventually into pure TPA and EG monomers. Kinetically, the reaction is modeled as first order with respect to PET concentration. By utilizing a catalyst to PET mass ratio of 1 to 67, zinc acetate lowers the activation energy barrier to 80.94 kJ per mole, yielding a rate constant of 23.0259 per second. This gives us a massive operational advantage, enabling high conversion while completely eliminating equipment corrosion and downstream chemical neutralization.
This slide summarizes the baseline material property used in Aspen Plus simulation for PET neutral hydrolysis. Water acts as the main stripping solvent and reaction medium, while the ethylene glycol is both a reaction product and part of the liquid solvent matrix. Terephthalic acid, or TPH, is represented in both solid and solid product form because it exists in different physics states throughout the process. Polyethylene terephthalate (PET) is modeled as a solid polymer substrate to represent the unreacted polymer feed, and the zinc acetate dehydrate is included as the catalyst in trace amount. The molecular weight, boiling point, and phase rule shown here were used to define the thermodynamic behavior and separation performance throughout the process simulation. This slide explains the solubility behavior of terephthalic acid in the reaction system. TPA has very poor solubility in both water and ethylene glycol. Therefore, after a reactor, the amount of TPA produced exceeds its solubility limit, causing the solutions to become the supersaturated and TPA crystal to form. To accurately predict the TPA solubility at different temperature, we collect the literature solubility data and feed the data in MATLAB using both linear and exponential model. The exponential model show a much better fit with a R-square value close to 1, so it was selected to develop the solubility correlation equation. This equation allows us to estimate the actual TPA solubility throughout the process and confirm that the crystallization after the reactor is expected and form the basis for the downstream solid liquid separation design. This table summarizes the physical and safety property of all process material. Among them, ethylene glycol is the primary flammable component, while the PET, TPA, water, and the catalyst are generally non-flammable under normal operating conditions. These properties were used as the basis for equipment selection and the process safety design. This flow diagram shows the overall PET neutral hydrolysis process, where PET is first mixed with the water in the CSTR reactor, where the PET is converted into the terephthalic acid and the ethylene glycol. Since TPA has a very low solubility, the reactor effluent is immediately sent to the crystallization sections. This allows the TPA crystal to form clearly, and the unreacted PET is separated in the following solid liquid separation state. By removing the solids particle as early as possible, the process minimizes the slurry transport through the downstream equipment, reducing the risk of solid accumulation, pipe breakage, and operational issue. The remaining liquid stream is then processed to recover ethylene glycol and recycle water back to the process. Overall, the process converts 1000 kg per hour of waste PET into approximately 780 kg per hour of TPA and 333 kg per hour of ethylene glycol while maximizing water recycle to reduce the fresh water consumption. This is our process flow diagram, and we will mainly focus on the mass balance and energy balance in the next slide. This table represents the overall mass balance for all process streams in the PET neutral hydrolysis process. Starting with the stream S1, 1000 kg per hour of PET is fed into the process. The recycled water is supplied through the stream S2 and S6, contributing 99.95 kg per hour and 699.76 kg per hour respectively, while only 169.84 kg per hour fresh backup water is introduced through the stream S5. After crystallization, stream S12 contains the maximum TPA recovery of 779.30 kg per hour, while the hydrocyclone underflow stream S13 recover 95.63 kg per hour unreacted PET for recycle. From the candle filter through the final TPA and EG product based on our steady-state assessment simulations, starting at S16, we recover 779.22 kg per hour of solid TPA product from the candle filter. This is our primary product stream. The filtrate S17 still carry most of the water and a small amount of dissolved EG, which we roll to the distillation column via mix 3, combining with the condensed flash vapor stream S20. The column V102 separate this into the overheat water stream S22, which we cool and recycle back to the reactor feed through the splitter S25 and S26, and the bottom stream S27, which carry our second product, ethylene glycol. Finally, S28 is our finished EG product at 294.91 kg per hour, cooled down to 25 degrees Celsius. The key takeaway: every stream here close consistently, water is recycled, and both TPA and EG leave the process as clean quantified product stream. This table is our enthalpy reference for all 28 stream, temperature, pressure, mass flow, and enthalpy flow straight from the S1 plus is the foundation every equipment duty in the next section is calculated from. Two quick notes. S9, the reactor effluents come from a combined reactor crystallizer block with model R101 and the crystallizer together as one RCSTR to properly capture TPA precipitating out, since it's barely soluble in water. And you can see our fresh feed S1 and S5 plus the 3 stream leaving the battery limit, our reactor PET purge, TPA product, and EG product. I won't walk through every row. This is our data reference. Next, we will build the equipment energy balance from it. This table gives the calculated duty for every unit operation: pump, heater, reactor, separator, distillation column, and so on. Check against our original equipment list. Almost everything matched within normal rounding. Two items needed a closer look. First, the reactor duty. Our original equipment list show negative 751.92 kilowatt, but the actually represent the reactor and crystallizer lumped together. From an earlier model, splitting them out, we get negative 606.8 kilowatt for the reactor alone and negative 145.1 kilowatt for the crystallizer. And those two sum right back to the original negative 751.92 kilowatt, so both numbers are correct, just now properly separated. Second, the crystallizer positively duty of 185.36 kilowatt doesn't mean heating. Temperature actually dropped from 112 to 90 degrees Celsius. That positive value reflects the heat of crystallization as TPA precipitate out, which is included in Aspen and enthalpy data. Overall, our total heating and cooling duty balance to within 0.03 kilowatt, essentially zero, confirming the energy balance is internally consistent across the whole process. This slide summarizes the utility duty estimate for our major heat changer used for costing estimation. We use the 3 utility: hot oil for the feed heating, cooling water for condenser and cooler, and the medium pressure steam for the column boiler. The largest duty are the V102 boiler at 8,629 kilowatt using steam, and the condenser at 8,370 kilowatt using cooling water. These dominate our utility cost. Total pump work is small, just 23.8 kilowatt, so it's normal supply as electrical power rather than a utility stream. This flow rate represents closed loop circulation, not fresh utility consumption, and will be finalized against actual plant utility condition.
Good day everyone. Today I'll take you through our engineered equipment specification for our PET neutral hydrolysis process. We begin in the primary reaction loop. Our continuous stir tank reactor RCSTR1 operates under extreme conditions 240 degrees Celsius and 32 to 40 bar using water and a zinc catalyst to sustainably break down PET without excessive chemical waste. According to our spent solid liquid equilibrium calculation, this yields a significant PPA precipitate split of 602 kg per hour of solid versus 180 kg per hour dissolved. To manage this, the stream enters our letdown vessel Flash 1 where an abrupt pressure drop down to 1.01 bar isolates flash vapors and provides natural auto-refrigeration cooling. This energy-saving step lowers the thermal load before entering our forced circulation crystallizer CRYST1, providing the essential residence time for the safe TPA crystal nucleation without fouling our pipelines. Moving on to our primary solid liquid separation train, to handle the output slurry, we first implement a centrifugal hydrocycle. This unit leverages a massive 13 times size difference to separate large, unreacted PET flakes measuring up to 12,000 microns from the final 50 to 150 micron TPA crystals. Next, the liquid stream is routed to filter 1, which is configured as a parallel duty and standby multiple candle filter array. Because our high total throughput of over 9,000 kg per hour exceeds the single element capacities, this split layout ensures one unit filters continuously while the other safely cycles through batch washing and cake discharge. Finally, the continuous filtered stream feeds into our red frac distillation column, which performs high purity fractionation to recover clean water overhead and recycle ethylene glycol from the base. Next, let's look at the auxiliary systems maintaining our plant's thermal and hydraulic balances. Feed preheaters liter 1 and 2 utilize hot oil to efficiently elevate incoming process liquid to our 240 degrees Celsius reaction target. On the cooling side, our process chillers and condensers utilizes standard plant cooling water with a conservative 0.1 bar allowable shell side pressure drop to knock down flash vapors. For high pressure slurry delivery up to 35 bar, we employ a heavy duty triplex piston diaphragm positive displacement pump to resist the abrasive 50% solid PET feed. For clean solid free lines, we specify Grand Force CRM multi-stage centrifugal pumps for smooth head pressure transport, while standard centrifugal transfer pumps PM3 and 4 handle intermediate loop where solid contents are low enough to avoid erosive impeller wear. Let's take a closer look at the exact mechanical anatomy of our flash drum separator, which handles the complex three-phase mixture. The vessel is engineered into 3 distinct zones to optimize separation and ensure plant safety. The top vapor emanation zone features a wire mesh demister pad that forces rising and strained liquid droplets to coalesce, and also gravity drain preventing downstream condenser burning. In the middle kinetic disengagement zone, a tangential inlet diverter and splash baffle absorb the massive kinetic energy from the inlet pressure drop, redirecting the stream into a safe downbound centrifugal wall flow. At the bottom, a steep angle conical boot forces the precipitating TPA solid crystals to slide continuously toward the outlet nozzle, explicitly avoiding the dead zones or catastrophic line plugging common with standard flat heads. This slide details our rotational equipment metrics across the key process areas. Pump 1 and 2 face completely different stream profiles, demanding entirely different mechanical setups. Pump 1 handles the aggressive 50% PET flake and water slurry moving from atmospheric pressure up to 36 bar. Standard centrifugal pumps fail rapidly here, so we utilize a triplex piston diaphragm pump to provide the immense mechanical force required without internal erosion. Pump 2, our high pressure liquid pump, handles pure water and liquid reactants. Since it is solid free, a vertical multi-stage Grand Force centrifugal pump provides highly efficient head pressure without the pulsation risk of a displacement pump. Intermediate pump 3 and 4 handle trace TPA solids where upstream classification has eliminated heavy abrasive risk, allowing cost-effective standard centrifugal unit to operate safely. To wrap up our technical design review, this table summarizes our engineered pump decision logic. The selection is determined dynamically by 2 inputs, the process fluid state and the required system pressure. When the fluid is an abrasive slurry with high 35 bar target, a triplex piston diaphragm positive displacement pump is mandatory to overcome the pressure ceiling and resist internal erosion. When the fluid is clean and requires high distribution head, a multi-stage centrifugal unit delivers continuous flow without operational pulsations. Finally, when abrasive elements are mitigated post-separation, low pressure intermediate requirements are safely and economically made using standard centrifugal impellers. This logical alignment ensures both process safety and minimized capital expenditure across the plant's life cycle. This slide shows the instrument control system for our process flow diagram. Starting from the feed section, the feed pumps use flow indicators and flow alarm to monitor the slurry and water flow, while pressure indicating controllers maintain the required discharge pressure and protect the pump. Next, the feed heaters use temperature indicating controllers to regulate steam flow, ensuring the feed reaches the desired temperature before entering the reactor. In the reactor, flow indicating controllers control the feed flow rates to maintain the correct reactor ratio and residence times for efficient reaction. The flash drum uses a level indicating controller to maintain the liquid level by adjusting the outlet valve. The cooling water condensers use temperature indicating controllers to keep the outlet temperature at desired value. Finally, the distillation column is controlled using pressure level and flow indicating controllers to maintain stable pressure, liquid levels, and product flow, ensuring efficient separation. Overall, these control systems provide safe, stable, and efficient plant operation. Let's look at the comprehensive instrument list for our process. Because we have a full inventory here, I'm going to point out the most important control loops that drive our plant stability. Starting with section A through C, feed lines for both PET slurry and water-free lines, we have flow indicators and coupled with pressure controllers. These work alongside safety isolation valves and spillback valves to manage raw material delivery.
The critical reactor feed crucially here temperature loops and throttle the steam valves to preheat our lines, which directly impacts reaction kinetics. This works hand in hand with flow loops and to precisely regulate the stoichiometric feed rates into the reactor via inlet valves. For flash dump B101, to finish this section, level controller adjust the liquid outlet valve to maintain our inventory balance. Moving into section E and F for vapor recovery and distillation. For cooling and condensing, we track thermal efficiency via 3 sequential temperature loops: TIC103 for flash vapor condenser, TIC104 for the EG product cooler, and TIC105 for the recycled water cooler. Each of these control its own cooling water valve, TCV103, 104, and 105. The critical distillation columns, the core focus on this is maintaining the strict mass and pressure balance of column B102. Overhead column pressure is tightly secured by TIC103, controlling the condenser valve TCV103. Volumetry balance is handled by the reflux drum loop LIC102, the delayed reflux flow speed loop FYC103, and finally the column bottom level loop LIC LCV103. By pairing highly responsive 4 to 20 MA electronic transmitter with reliable 3 to 15 piece SIG pneumatic control valve, this full configuration ensures our entire process remains stable and automated from end to end.
These are all sources can refer from our project, and thank you for listening.